Bem-vindos ao nosso espaço, um mergulho profundo nos assuntos mais interessantes de esportes, ciências e temas gerais do momento. Aqui você vai encontrar conteúdo de qualidade, com análises empolgantes e descobertas fascinantes que vão expandir seus horizontes. Nossa missão é trazer informação relevante de forma dinâmica e descontraída. Queremos que você faça parte dessa jornada incrível de conhecimento e diversão. Se gostar do nosso conteúdo, não esqueça de deixar seu like e se inscrever no canal para não perder nenhuma novidade. Ative o sininho também. Aproveite!
If you love science, don't forget to like and subscribe. When we think about the great migrations of the world, we usually picture wildebeests crossing the Serengeti or whales traversing the vast reaches of the Pacific. But there is another migration, far more massive and arguably more critical to life on Earth, happening right under our noses, and often, right inside them. This is the global movement of pollen. While it looks like simple dust, the journey of a pollen grain from an anther to a stigma is a masterpiece of high-stakes physics. At the heart of this journey lies a phenomenon known as the tribological trap. Tribology is the branch of science and engineering that deals with interacting surfaces in relative motion. It includes the study of friction, lubrication, and wear. While we usually apply it to car engines or hip replacements, nature has been a master tribologist for hundreds of millions of years. For a plant, the challenge of reproduction is a delicate balancing act of adhesion. A pollen grain must be loose enough to be picked up by the wind or a passing insect, yet sticky enough to stay attached during transport, and finally, it must possess the perfect grip to latch onto its destination, the female reproductive organ of another flower. The architecture of a pollen grain is where the physics gets fascinating. If you look at pollen under a scanning electron microscope, you'll see a world of bizarre, alien-like shapes. Some grains are smooth, others are covered in hooked spikes, and some are riddled with deep pits. This outer shell, called the exene, is made of spiropollenin, one of the most chemically resistant organic materials known to man. But it isn't just for protection, it's a tactile interface designed to manipulate friction. The tribological trap refers to the way plants use molecular forces to control these interactions. One of the primary players here is the van der Waals force, a weak attraction between molecules that becomes incredibly powerful at the microscopic scale. To manage these forces, many plants produce pollenkit, a sticky, lipid-rich coating. This substance acts as a biological lubricant and adhesive simultaneously. It reduces friction to allow for easy release from the parent plant but increases viscosity to ensure the grain traps itself onto a pollinator's fuzzy back or the receptive surface of a stigma. But the trap is even more sophisticated than simple stickiness. Recent research has shown that pollen grains use electrostatic charges to bridge the gap between surfaces. As a bee flies through the air, it builds up a positive charge. Flowers, being grounded, tend to have a negative charge. When the bee approaches, the tribological properties of the pollen change. The friction of the air and the electrical gradient create a jump, where the pollen grains are literally pulled across the void, snapping into the trap of the flower's reproductive system. Climate change is adding a new layer of complexity to this microscopic dance. Tribology is highly sensitive to environmental conditions like humidity and temperature. In high humidity, the moisture can act as a bridge, increasing capillary forces and making pollen too sticky to fly. In overly dry conditions, the pollen might lose its grip entirely, failing to latch onto its target. As global weather patterns shift, the tribological trap that has dictated the spread of flora for eons is being recalibrated. Some species may find their pollen can no longer bridge the distance, leading to a collapse in local biodiversity, while others might find new advantages in the changing friction of a warmer world. Understanding the molecular friction of pollen isn't just an academic exercise. It has massive implications for agriculture, allergy medicine, and even the design of new microadhesives. By studying how nature solves the problem of controlled stickiness, engineers are learning how to create materials that can grip and release at the molecular level without the need for traditional glues. The next time you see a cloud of yellow dust in the spring air, remember that you're witnessing a billion microscopic calculations in motion. Each grain is a tiny ship navigating a sea of friction, guided by the laws of tribology to ensure the survival of its species. The global spread of flora isn't just a biological success. It's a physical one, governed by the invisible forces that keep the world turning. For more incredible facts like this, don't forget to subscribe and turn on notifications.